Okay folks, so now we're ready to talk about the first principle of superposition for homogeneous equations. So it says let's let L be the nth order linear differential transformation, and suppose y1 and y2 are both n times continuously differentiable. I can take the derivative n times and that nth derivative is continuous. And further, suppose when I do L to y1 it outputs a 0. And also when I do L to y2 it outputs a 0. Then superposition, this first principle of superposition, states that any linear combination of those two solutions will also spit out a 0. Okay? So, for example, for our linear operator up here, when I say L of y1 is equal to 0, if we were talking about this linear operator up here, that's saying that 3y1 double prime minus the sine of x, y outputs a 0. y1 outputs a 0. So if I plug y1, take its second derivative, multiply it by 3, subtract from that the sine of x times that y1, it outputs a 0. Same thing if I do it to L2. If I do 3 y double prime of y2 minus the sine of y2, that's going to output a 0. So that's this statement is this expression right here. This statement is this expression right here. What superposition is claiming is that any linear combination of those two solutions will again output a 0. So, for example, if C were 2 and C1 were 2 and C2 were minus 5, then 2y1 minus 5y2, if you do this linear transformation to that sum, you're going to get out a 0. Okay? Now the thing to keep in mind is, what is this equation right here? If L of y1 outputs a 0, that corresponds to what type of an equation? Well, yeah, it's second order and it's linear, but what I want to highlight is if L of y1 outputs a 0, that means y1 solves a homogeneous equation. Likewise, y2 solves a homogeneous equation. And what we're claiming then by superposition is that any linear combination of those two solutions is also a solution to the homogeneous equation. So let's go ahead and look at number 13 here to put that into practice. We're going to assume y1 and y2 both output a 0 when you plug them into this particular differential operator. And you can check that. When you take the derivative twice of this, you'd have 9e to the 3t minus 3e to the 3t minus 6e to the 3t, and sure enough that outputs a 0. You could check y1 similarly. Okay? So if I know that I've got two solutions to the homogeneous equation, what we're claiming is that any linear combination of those two solutions is also a solution to the homogeneous equation. So I'm going to check that. I'm going to check it two different ways. The first way is sort of the long way, but I'd like to do it because it will fit, it should make more sense. And then the second way is a shortcut using this linear operator notation. So let's look at y of t and show that it solves this homogeneous equation. So if we take y of t and plug it in, we would take the second derivative of our y of t, which is 4e to the minus 2t plus 5e to the 3t. And we would subtract from that the first derivative, ddt of 4e to the minus 2t plus 5e to the 3t. And we would subtract from that 6 times just y of t, 4e to the minus 2t plus 5e to the 3t. And if this is going to solve the homogeneous equation, what does this whole thing need to simplify down to? It needs to simplify down to 0. So rather than actually computing the derivatives, though, I'm going to use my knowledge that y1 and y2 solve the homogeneous equations in order to arrive there. So I'm not actually going to apply the second derivative operator to e to the minus 2t, but I am going to distribute the second derivative operator to both terms in this sum and factor out constants. So I can rewrite this as 4d squared dt. That should have had a squared on it. Sorry about that, folks. d squared dt squared of e to the minus 2t plus 5 d squared dt squared of e to the 3t. Same thing here, we get minus, I'm going to factor out the 4, minus d dt of e to the minus 2t, minus 5 d dt of e to the 3t. And I'm not going to multiply this 6 times this 4 or this 6 times this 5, but instead I'm going to go ahead and rewrite this as minus 4 times 6 e to the minus 2t minus 5 times 6 e to the 3t. Now what have I got? Well, I've sort of got a mess here, but let's go ahead and group together all of the e to the minus 2t terms. Notice that all of the e to the minus 2t terms that show up here, either taking the derivative or show up on their own, have a factor of 4. So I'm going to pull that factor of 4 out. That gives me 4 times d squared dt squared of e to the minus 2t minus d dt of e to the minus 2t minus 6 times e to the minus 2t. Okay. So all of this is, I've taken together all of the e to the minus 2t terms, collected them together, and then factored out that common factor of 4. Okay. I can do the same thing here. I can factor out this 5 from all of the e to the 3t terms, and I'm left with d squared dt squared e to the 3t. Is it a positive 3t? Yes, it is. 3t minus d dt of e to the 3t minus 6 e to the 3t. Okay. Well, this is the linear operator applied to e to the minus 2t. That is, I already said that this solves the corresponding homogeneous equation. If I were to plug e to the minus 2t into this expression here, I've said that it's going to output a 0. So I know that this is 4 times 0 plus 5, and all of this is the differential operator applied to e to the 3t, and I've already said if I plug in e to the 3t, it's going to output a 0. So times 0. This gives me 0. Okay. So if this didn't make sense to you, I encourage you to work back through it one more time. Pause the video, work back through it. But let me show you how we can now use this linear operator notation to simplify this procedure greatly. So this is the benefit of this linear operator notation. So I'm going to look at L of 4e to the minus 2t plus 5e to the 3t. And now that we've said that L is a linear operator, we can actually save a whole lot of time here. In my first step, and I could actually do both these steps at once, but I'd like to separate them this time, I'm going to distribute the linear operator over the sum. So I get L of 4e to the minus 2t plus L of 5e to the 3t. Why can I do that? Because I know this is a linear operator, and so it distributes over the sum of these two functions. Further, since L is a linear operator, I can factor out the constant of 4. Oops, I dropped the e there. Let me just clean that up real quick. But what do we know about L of e to the minus 2t? Well, we said that it satisfies the equation that when I plug it into the differential operator, it's going to spit out 0. So I get 4 times 0 plus 5 times 0, giving me 0 at the end. So this is working with this new linear operator notation. If I lost you on this, use this as your guide. But this shows how the linear operator notation greatly simplifies working with some of these larger expressions. All right, in the next video we'll talk about the second principle of superposition.